Well, hi everyone. My name's Emma Turtelboom. I'm a grad student in the Department of Astronomy here at Berkeley, and today I'll be telling you a little bit about the sort of research I do on studying planet formation using observations of exoplanets and protoplanetary disks. But that's all a lot of jargon, so let's start off with just the first thing that comes to mind when we think of planets, and that is our own solar system. And, that's our home right there, the Earth. We have many observations of the planets in the solar system, as you can see from these images. They're not to scale, but are representative of some of the many observations we have of planets in our own solar system. But over the past few decades, it's become clear that exoplanets, which are planets that orbit stars other than our sun, are ubiquitous in our galaxy. There are many, many, many of them, and this was a huge surprise to astronomers. As of right now, there are over 5,000 exoplanets known outside our own solar system, and with such a big sample, we can actually start learning about sort of what might make the solar system special or unique, or actually not all that special and not unique. And so this is a really exciting field of study with lots of new data being collected all the time. And so first, for some background, I'll talk about two of really the workhorse methods of exoplanet detection used in the field today. The first is the transit method, and so this method takes advantage of the fact that based on their random orientation in space, planets sometimes pass between their host star and our line of sight looking from Earth. And what this does is, as the planet passes in front of the host star, it blocks a little bit of that star's light. And so we can't see the planet. This is an indirect detection method, since these stars are far away. These planets do not emit their own light. They're very, very faint. But so what we can see is this dip in the light curve, i.e. the brightness of the star with time. And that can indirectly tell us that there is a planet orbiting that star. The second method I'll talk about is the radial velocity method. And this method takes advantage of the fact that as a star is orbited by a planet, really what is actually happening is that they are both orbiting their common center of mass, represented by the plus symbol here. And this is an exaggerated kind of GIF for effect, but what this does is this, as the star, again, we cannot directly observe the planet, as the star kind of wobbles back and forth around its the center of mass of the system, the light from that star is periodically blue shifted and red shifted as the star moves towards and away from us. And so what we end up seeing is the spectral lines in the light that comes from that star, they are shifted over time. And you can basically measure that shift to make a plot kind of like this. And from that, you can infer that there is a planet or something else, but in my case, we care about looking for planets orbiting that star. And there are other methods that we use to find exoplanets, but these are really the two most prevalent ones, at least in the last few decades. And so what can we learn from these planets, from these observations, excuse me? These two plots show the population of exoplanets, confirmed exoplanets. They might be a little bit out of date, but you can see we know about a lot of them. On the x-axis in both plots, we see orbital period, so the time it takes the planet to orbit its star once. And then on the left-hand plot, on the y-axis, we have planet mass. And that is measured using the RV method, the radial velocity method that I just mentioned. And on the right, on the x-axis, we have planet radius. And here you might notice there's a lot of yellow points on this plot, which we don't see here. And that's because of a mission called the Kepler mission that really discovered thousands and thousands of planets. But we were only able to measure radius because it was a transit mission, so looking for those dips in stellar brightness. But okay, now we have these huge populations. Great. Well, this is not just an exercise in counting planets. Now we can actually start to do really interesting things like looking at, well, okay, are these planets the sizes that we expected them to be based on our own solar system? Are they at orbital periods that we expected? And things like that. And what we actually find is that there are many different types of exoplanets, more than we expected given our own solar system. So here again on the x-axis we have orbital period, and on the right we have size. And then on the left, on the y-axis. And then here on the right, you can see some solar system planets for reference. So here, this line corresponds to the size of the Earth. Then next we have Neptune, and finally Jupiter. And so what we find when we look at this population of exoplanets is that there are planets up here in this hot Jupiter regime, as it's labeled, that we don't see in our own solar system. We do not, Jupiter in our own solar system is far out. It has an orbital period of like 11 years. Whereas in a lot of exoplanet systems, we see Jupiter-sized planets that orbit at, with orbital periods of like a day, which is really not what we expected at all. We also see many of these sub-Neptune-sized planets, these types of planets appear to be much more prevalent than we expected, given our own solar system. And the kind of study of looking at, for these populations of planets, is called kind of exoplanet demographics, and there's really a lot of rich information that we can find in these population level analyses. And so another example of that is this phenomenon called the radius gap. And so here we're looking at the distribution, we're counting how many exoplanets there are of different sizes, ranging from just under the size of the Earth all the way up to 20 times the size of the Earth. And what we find is this like very clear bipedal distribution with two distinct populations of planets, and we call this smaller population super Earths, with a peak at around 1.3 Earth radii. So just a little bit bigger than the Earth, hence the name. And then we also have sub-Neptunes, which are just a little bit smaller than the size of Neptune. But we see this very clear gap, this radius gap, where there aren't a lot of planets with sizes of around 1.8 Earth radii. And on its face, that might look interesting, but kind of, okay, so what? But actually, the questions that this raises are really interesting when we think about planet formation. What can we learn about planet formation? What about planet formation theories can tell us why planets which are around 1.8 Earth radii just don't form? Is it possible that sub-Neptunes have these primordial atmospheres? They have thick layers of gas around them that they retain, while planets which form at around 1.8 Earth radii lose their atmospheres for some reason and become these kind of rocky cores that we see in the super Earth population? We don't know. And so by looking at these population level trends, we can start probing not only the state of the planet population as we observe it now, but how it may have been when these planets were forming. We can also compare other planetary systems to our own solar system. It appears that most exoplanets are in multi-planet systems. And then we can compare these systems as systems rather than just individual planets to our own solar system. And so this is a plot showing many multi-planet exoplanet systems. And there's a lot of information going on here, but what I want you to take away is that there's really a diversity, a huge variety of types of systems that we see. And I'll just highlight a few to illustrate the point. So first you can take a look at this one up here, TRAPPIST-1, which is a very well-known system because it hosts many planets. It hosts 7 planets, and they're all pretty similar sizes. The points are scaled according to planet radius, and they're all spread out pretty evenly within the system. But then if we look at another system, like Kepler-167, we can see here that there are 3 inner planets that are all roughly the same size, a large gap in period, and then a giant planet further out. Another example is KOI 351, where you can see, again, we start with smaller planets in the inner system, and then as you move outwards, the planets appear to get bigger. And so there are many trends like this that we can see now that we have this population of multi-planet systems, and from that we can start thinking about, well, what kinds of formation conditions, what kind of formation mechanisms, what kind of evolution mechanisms can lead to these results, to these outputs, if you will. And that's kind of a really interesting area of research at the moment. Something to note about these systems is that we cannot still directly compare them to our own solar system because of the region of parameter space that we're sensitive to. So for example, if you look at these plots, on the x-axis we have orbital period again. This x-axis only goes out to around 1,000 days, so, a couple of years. When we think of our own solar system, that doesn't even really get you out to the gas giants. So we're not sensitive to, the outer regions of these planetary systems. It may be that all of these systems have many, many more planets as you go even further out. And so our picture is a little incomplete. The great thing is that there are fantastic telescopes, both currently operating and to come in the future, that will hopefully allow us to probe the outer regions of planetary systems. So this is kind of a journey through time and some of the really flagship missions that we use to look at exoplanets, starting from the Hubble Space Telescope, Spitzer, Kepler, the TESS mission, which is currently operating, and JWST, which is currently operational, and looking also to the future, Cheops, Plato, WFIRST, which is now known as the Nancy Grace Roman Telescope, and all the way out to LUVOIR and HABEX. And these facilities will make us more sensitive to those outer regions and allow us to make more kind of apples-to-apples comparisons with our own solar system. But now that, once we have additional data, and even with the kind of limited picture we have now, when we observe planetary systems, as we do right now, we're only getting a snapshot. You can think of it as, getting one picture from one birthday. And if you take a birthday picture every single year, you will see a person changing and evolving. And similarly, we would love to be able to see how a planetary system and how planets evolve. Unfortunately, we can't wait around for that to happen. The timescales that planets form on are just far too long. You start with your molecular cloud that collapses to form a star, and you have your protostellar disk and then circumstellar disk forming a protoplanetary disk, and from this, after millions and millions and millions of years, we end up with the planetary systems that we can observe. And so if you look at this kind of pictorial representation, you can see that taking observations here, while it certainly tells us a lot, as we've seen, it doesn't tell us the full picture. And that's where images of protoplanetary disks come in. And this kind of area of research has really been revolutionized by the ULMA facility, which is a series of telescopes in Chile. And with these observations, we've been able to directly image protoplanetary disks, really in a systematic way, looking at you can see this kind of survey here for the first time, which is really exciting because we can see we are basically getting another birthday picture. We've had the picture at age 50. Now we're looking at the picture at age 15, and this can tell us we're starting to learn a lot about, well, what do we think the planetary systems that result from a disk that looks like this? We're trying to connect these different pieces together to get an idea of the kind of life cycle of these planets. And so this is really exciting to learn more. And so by connecting these different snapshots at different stages of planetary formation and evolution, we can put together all these different pieces to hopefully one day place our solar system in context and learn about kind of our place in the Milky Way and maybe beyond. So thank you very much. And that's it.